Today we're going to talk about section 3.6. Rational functions. Okay, rational ratio has to do with something that is comparing two expressions. So a rational function is of the form r of x equals p of x over q of x, where p and q are polynomials. So when we look at an example for a parent function, we're going to look at a parent function called f of x equals 1 over x. So this is a constant, and this is an individual variable of x. So we're going to graph that. Now this one we're going to graph by plotting points. Other ones we're going to do some other things with. So we're going to plot points by having an XY chart. So x, f of x. So we're going to put in -2, -1, -1/2. If I put in -2, 1 over -2 is going to give me a -1/2. If I put in a -1, 1 divided by -1 is -1. If I put in a -1/2, I get 1 over -1/2. So to divide a fraction is the same thing as multiplying by its reciprocal. So 1 times -2 over 1 gives us -2. Okay, so we're also going to try some other ones. We're going to do them over here. So we're going to try +2, +1, and +1/2. So if I put in a +2, I get 1/2. A +1, I get 1. Multiplying by the reciprocal give me a +2. So we're going to plot those points. So I start out with -2, -1/2. -1, -1, -1/2, -2. And over here I plot 2, 1/2, 1, 1, and 1/2, 2. Now, when we look at this, we know that x cannot be 0 because that would be a restriction. X cannot be 0. So for x to be 0, we're looking at what kind of a line? We're looking at this vertical line. So that would be an asymptote, right? And we also know that y, there's no way y can be 0 either, because if I put 0 in the bottom, that makes this undefined. So this is also going to be an asymptote. Remember we said asymptotes were things that you cannot have, so we're putting a dotted line. So this is going to approach the asymptote but not cross. So we have 1 over x graphed that looks like this. Now we're going to talk about some things. This one, as f of x goes to 0, as this goes further and further out, it gets closer and closer to 0, right? So f of x approaches 0 as x goes to what? As it goes further and further out, x is going to positive infinity. If we talk about this one down here, we're talking about f of x is the y value So f of x is going to approach negative infinity as x approaches 0 from the negative side. Okay? So f of x would be going down. On this one up here, we've got f of x going to 0. So it's going to 0 as x goes to negative infinity. And this one up top, f of x is going to infinity, y is going to infinity as x goes to 0 from the positive side. So we have our graph, f of x equals 1 over x. So we know these lines, x equals 0 and y equals 0 are asymptotes. Okay, so now we're going to look at another example using that idea of the parent function. R of x equals 2 over x minus 3. Now, we're going to take the 2 out of this, so we're going to rewrite it as 2 times 1 over x minus 3. So what happens is this bottom number, x minus 3, if we think about what this original picture looks like, these are my two asymptotes, right? So when we have it inside the function does what? Moves it left or right. So this would be a minus 3, so we would think it would move it to the left, but inside the function is the opposite of what you'd expect, so it's going to move it to the right, 3. So when I have my graph, instead of my asymptote being here, it's going to be 1, 2, 3 to the right. So my new graph would look something like this. Okay, because we talked about transformations, right? So this would be a transformation. We can distribute this out, this 2 out of the top. Okay, we're going to look at another example. S of x equals 3x plus 5 over x plus 2. Now, we're going to rewrite this in a different way. So we're going to take the 3x plus 5 and divide by x plus 2. So we learned how to do long division. So what times x gives me 3x is going to be a 3. So then I distribute 3 times x is 3x. 3 times 2 is 6. Subtract. 3x minus 3x gives me 0. 5 minus 6 gives me a negative 1. So now when we look at this, we're going to rewrite it as 3. And then plus the remainder, negative 1 over x plus 2. So we have it written down now in a different format. So we have s of x equals 3 plus negative 1 over x plus 2. Now, when we talked about the transformations before, remember we said that the transformations, numbers on the outside of the function, so this 3 is outside of the function, is going to move it vertically. So that means we're going to go up 3, so that's up 3. The negative in front of the function, so this would be like a negative in front of the function, reflects it across the x-axis. So up 3, reflect over x-axis. And then the plus 2, what is the plus 2 going to do? Well, the plus 2 is inside the function, so it's the opposite of what you'd expect. So we know that it's going to be left 2. So we're going to go back to our parent function. So our parent function looks like this. So this would be my y equals 1 over x. So this is what I'm starting with for my transformations, right? So we're going to move it up 3 and left 2. So we're going to go over here and up 3 and left 2. So that took care of the up 3 and the left 2, but reflecting over the x-axis. So instead of it starting up here, it's going to start down here. So we're going to have this graph that looks something like this. Because normally this would go down here and this would go up here, but then we reflected it. So here's my y equals 3 and my x equals -2 for my asymptotes. Give everybody a chance to catch up to that point first. Now, as the expressions get more difficult, we come up with a formula for the horizontal asymptotes. So our normal expression, and if you want to look this up, it's on page 300 in your textbook. Our normal expression is going to be a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus and so forth, right? And then we end it down here. We're going to call the next one, the one that's on the bottom, we're going to call it b sub m x to the m plus b sub m minus 1 x to the m minus 1 and so forth. Now obviously we end it down here. But the thing that we're looking at for this formula is we're looking at just the two leading terms. So m and n are the degree of these polynomials. So if n is less than m, so if this top number is less than this bottom number, then r is going to have a horizontal asymptote. Of y equals 0. If n is equal to m, so if these two numbers are the same, then the horizontal asymptote is y equals a sub n over b sub m. So what did we do? We just took the numerical coefficients off of the leading term, and that would be my horizontal asymptote. If n is greater than m, then there is no horizontal asymptote. Okay, so give everybody a chance to get that written down. Okay, so we're going to look at an example where we find the vertical and the horizontal asymptotes. Okay, so our example is going to be r of x equals 3x squared minus 2x minus 1 over 2x squared plus 3x minus 2. Now, our vertical asymptotes, so that's the things that x cannot be. So when we have a fraction, we know that the denominator cannot equal 0. So our vertical asymptotes come from the denominator. So vertical asymptotes are where the denominator is equal to 0. So we're going to take 2x squared plus 3x minus 2. And we don't want that to be 0. So we're going to factor that into two sets of parentheses. So we get 2x and x. Negative 2, so one's got to be positive, one's got to be negative. So we're going to make this be negative 1 and a plus 2. So let's check it out. 2 times 2 for the outside gives me 4x. Negative 1 times x gives me negative 1, so 4 minus 1 gives me my 3x, which I needed. Now we know for a zero product rule then that 2x minus 1 cannot be 0. And x plus 2 cannot be 0. So that means x cannot be, adding 1 and dividing by 2 would be 1/2, and x cannot be negative 2 by subtracting 2 over. So these are my vertical asymptotes. Now for our horizontal asymptote, we look at our formula that we have written down. So my n and my m are equal. So n equals m, 2 equals 2. So that means that I do what? I take off the coefficients of the leading terms. So my horizontal asymptote is y cannot equal 3/2. So horizontal asymptote and vertical asymptote. Vertical, denominator cannot be 0. Horizontal asymptote, you can use this chart. All right, so now let's put some things together that we know and see about doing a graph. So everybody caught up at that point? So we're going to start out with graph r of x equals 2x squared plus 7x minus 4 over 1x squared plus x minus 2. So the first thing we're going to do is factor the numerator and the denominator. So we're going to have r of x equals so 2x squared is going to give me a 2x and a 1x. Then I've got to decide 4 and 1 or 2 and 2, but I have a 7. So I'm going to make this be a 4 and this be a 1. This would give me 2 times 4 is 8. 1 times x is 1, so 8 minus 1 gives me 7, so I need the larger number to be positive. So the 4 is going to be the plus, and then 1 is going to be the minus. On the bottom, I have 1x squared, the denominator, so I have x and x to be x squared, 2 and 1. So I'm going to make this be 2 and this be 1. I've got a positive 1, so that means the larger number has to be positive, so the 2 has to be positive and the 1 has to be negative. Now, when we look at this, we can find the vertical and the horizontal asymptotes, or we can also find the x and the y intercepts. So we're going to do, the first thing we're going to do is to find the x-intercepts. So x-intercepts is where y equals 0. To make a fraction equal to 0 is when the numerator is equal to 0. So if I set 2x minus 1 and x plus 4 equal to 0, then I get x equals 1/2 and x equals -4 using zero product rule. So those are my x-intercepts. So I've got 1/2 comma 0 and -4 comma 0. So these are my x-intercepts. Now the y-intercepts are where x equals 0. So if I go back to my original problem and set all of those things, those x's equal to 0, I get 2 0 squared plus 7 times 0 minus 4. And this part we could have done in our head, but for notes purposes, 1 times 0 squared plus 0 minus 2. So these zeros all go to 0, and we're left with -4 divided by -2. Negative divided by negative is +2. So my y-intercept is going to be 0, comma 2. So now we have x-intercepts and we have the y-intercepts. So now we're going to find the vertical asymptotes. So the vertical asymptotes is where x cannot be. So that's where we're setting the denominator. Cannot be 0. So we have x plus 2, x minus 1 cannot be 0. So that means x plus 2 cannot be 0, and x minus 1 cannot be 0. So we get x cannot be -2, and x cannot be +1. So these are my vertical asymptotes. Okay, my horizontal asymptotes. So we're going to look at our two m and n, so they both match. So if they both match, then we know that it's going to be the coefficients off the front. So y cannot be 2 over 1, or y cannot be 2. So this is my horizontal asymptote. So we're going to go ahead and graph the things that we know. So we have our x-intercepts and our y-intercepts. So we're going to have 1, 2, 3, 4 this way. So our x-intercepts 1/2 0. So this would be 1/2 0 and -4 0. Our y-intercepts is 0, 2. Then we have our vertical asymptotes. X cannot be -2. So we have a dotted line for the vertical asymptote. And x cannot be 1. The horizontal asymptote, y cannot be 2. So now we're going to have some test points. So the next thing we're going to do is test points. Because we want to know whether it goes up or whether it goes down. So our test points we're going to pick are things within each of those intervals. So I might want one here, so that'd be 1, 2, 3, so x equals negative 3. And then we need one here, negative 1. And then we need one up here, would be 2 and 3. So we plug these into our original problem into the calculator, and I'm just going to go ahead and tell you what you come out to be. So we get negative 1.8, 4.5, 4.5, and 3.5. So we're going to graph those things. Negative 3, almost negative 2, so 1, 2, 3, negative 2 would be down here. Negative 1, 4.5. 3, 4.5 would be approximately here. And then we have 2, 4.5. 2 would be 4.5. And 3 is 3.5. So we're going to see what our graph is doing then. This is going to come down through here. And this is going to approach the asymptote going up here. This one's going to approach the asymptote, go through that dot, and then come back down to approach this asymptote. And then this one's going to do the little curve again. So give everybody a chance to catch up to that point. Now, you'll notice that here was an asymptote, and we crossed the asymptote. So on page 304, I encourage you to look it up on page 304. It talks about that it's a misconception that a graph cannot cross the horizontal asymptote. So this is talking about the horizontal asymptote. Okay, we're going to try another example so that you can see another one worked out. Okay, this one's going to be from the textbook. We're going to do number 51. Page 308. So it gives us s of x equals 2x minus 4 over x squared plus x minus 2. So it wants us to graph. So we're going to do like we did last time. We're going to find the x-intercepts first. So we said the x-intercepts was to set the numerator equal to 0 because x-intercept has y equal to 0. So I've got 2x minus 4 equal to 0, add 4, divide by 2, x equals 2. So our x-intercept is going to be 2, 0. So when I grade these, notice that I'm going to be putting each of those as a separate answer. Second thing we found was the y-intercept. The y-intercept is going to be x equal to 0. So if I go through and make all the x's equal to 0, what do I end up getting? So I got 2 times 0 minus 4, 0 squared plus 0 minus 2. So these would be all these zeros, so I would get a 2. So my y-intercept is y equals 2. So I'm going to get 0, 2. The vertical asymptotes would be the next thing we're looking at. Now remember, we said vertical asymptotes were what? Vertical asymptotes are where the denominator cannot be 0. So we're restricting our restrictions. So we have x squared plus x minus 2. So we factor that into 2 sets of parentheses, x and x, 2 and 1, positive 1, so it's got to be a positive 2 and a minus 1. Zero product rule then, we'd have x plus 2 cannot be 0, x minus 1 cannot be 0, so x cannot be negative 2, and x cannot be a positive 1. So those would be my vertical asymptotes. All right, the next thing we want to find is the horizontal asymptotes. So we look up here and we see that this is going to be of 1 and this is going to be a 2. So since n is less than m, 1 is less than 2, then we're going to have y equals 0 as my horizontal asymptote. So we're going to start out by graphing those things that we know. So we're graphing the x-intercept. Well, let's make some marks first. So our x-intercept's 2, 0. Our y-intercept is 0, 2. Our vertical asymptotes, x cannot be negative 2. X cannot be a positive 1. And then we're going to plot our horizontal asymptote. Y cannot be 0. So we're going to do it just a tad bit above, just so we can see that the dotted line is there. So now we have to have some test points. So we have negative 3 for down here, negative 1 between here. This would be between 0 and 1 is 1/2. And then 1, 2, 3, because we have a point here, we're going to go to 3. And then we're going to try one more down here in negative 4. So I'm plugging that into my original problem, right? So I've got 2 times negative 3 minus 4 over negative 3 squared plus negative 3 minus 2. And we put that into our calculator, and that gives us a negative 5 over 2. I'm going to go ahead and help you with this one. Negative 1 is 3. 1/2 is 2.4. 3 is 0.2. And negative 4 is negative 1.2. So we're going to go ahead and graph. So this negative 5/2 would be negative 2 and 1/2. So I go to negative 3. 1, 2, 3. And I go down to negative 2 and 1/2. And I have a dot right there. Negative 1, 3. So negative 1, 1, 2, 3 is going to go up. 1/2, 2.4. 1/2, 2.4. 3.2. negative 4, negative 1.2. Okay, so we can see what this is doing. It's coming up here, across like that, and then coming down here. And then this one's going to approach that asymptote and approach this asymptote. So we got an idea of what steps we need to take. Now, we've seen all these previous examples. We found the x-intercepts, y is equal to 0, setting the numerator equal to 0. The y-intercept is setting the x equal to 0. The vertical asymptote, the denominator equal to 0, and the horizontal asymptote based on the degree of the numerator and the denominator. So that gives us of the steps that we're going to take. Now, some of them do not have a horizontal asymptote, but some of them have a slant, and we're going to talk about that in a minute. But also some of them have holes where you can't have. So we're going to look at holes in x. So if the numerator and the denominator have a common factor, then we may cancel that factor, okay? But we call this value at where we cancel it, we call that a hole. So we're going to look at an example. Okay, so the first thing we're going to do is we're going to factor. So we're going to take out an x squared, and this is going to give me x minus 2, and this is going to give me x minus 2. Now, if I cancel the x minus 2's out, we know that this x minus 2 is going to be a place where there's going to be a hole. So I cancel those out, so x minus 2 equals 0 is a hole in the graph. Now, why is it a hole in the graph? Okay, so if I add 2 to both sides, I get x equals 2. If I plug in x equals 2, what's going to happen? 2 is going to be make this 0 on the top in the numerator, and this is going to be 0 on the bottom, the denominator, which 0 divided by 0 we can't have, right? So that's why it's a hole. Holes are where you cannot have that dot. So we cannot have x equals 2 because it would cause that to come out to be 0. So we're going to go ahead and cancel those out, and we're going to get r of x equals x squared. Now we know what r of x equals x squared looks like. That's going to be a parabola, right? But we also know that if I plug in my 2 for my hole, that's going to tell me where my hole is. So I've got y equals 2 squared, because that would be y equals x squared. So I'm going to get 4. So my hole is going to be at the point 2, 4. So we're going to graph the parabola. Now we know how to graph a parabola because that's our parent function. So we're just going to do that. So what do we say? 2, 4 was our hole. So 2, 4 is going to be the hole. So we have a parabola that looks like this. But when it comes up here, it jumps across that hole. It's supposed to go through the line. So the idea is you factor, you decide what's going to be canceled out, and that becomes where your hole is. And then you find the y value for that x. So that gives us our hole. Give everybody a chance to catch up to that point. Okay, we're not going to take time to graph this next one, but we are just going to go ahead and find out where the hole is. So we're going to just find the whole first. So I have r of x equal x squared plus 4x minus 5. And I've got x squared plus x minus 2. So again, we factor the numerator and the denominator before we start. X and x, 5 and 1, subtract to be 4, so the positive number has to be the 5, and the negative has to be the 1, because the larger number has to be positive. You got x and x, 2 and 1, so again, positive 1, so the larger number has to be positive, and this has to be negative. So now, what do we see? We see that x minus 1 it can be canceled out. So x minus 1 equals 0, x equals 1 is the whole. But if I put x minus 1 into these two together, I'm going to get the 0 over 0 thing. So I have to cancel the whole out first. And I get x plus 5 over x plus 2. And I plug in the 1. So when I plug in the 1, I get 1 plus 5 over 1 plus 2 gives me 6 over 3. So my whole is going to be at 1, comma, 6 divided by 3 is 2. So my whole would be at 1, comma 2. So we would go about graphing the same way we did with those other steps. X-intercepts, Y-intercepts, asymptotes, but the whole would be where we make sure we put an open circle. So we're okay with that? Okay, the next thing we're going to look at is the last section, would be on slant asymptotes. So we're going to start out with an example. We're going to graph r of x equals x squared minus 4x minus 5 over x minus 3. Now, in order to have a slant asymptote, the degree of the numerator is got to be 1 more than the degree of the denominator. So see how this is 2 and this is 1? So the degree of the numerator is 1 more than the degree of the denominator. So make sure you write that down. Degree of numerator is 1 more than the degree of the denominator. Okay, so in order to have a slant. So what we're going to do is we're going to take the numerator, x squared minus 4x minus 5, and we're going to divide that by x minus 3. So x goes into x squared, x, then I distribute x times x is x squared, 3 times x is negative 3x. Parentheses, subtract. X squared minus x squared is going to cancel out. Negative 4 minus a negative 3 gives me a negative 1x. Minus 5, drop down the next term. And so now I've got x times what gives me negative 1x would be negative 1. So negative 1 times x is negative 1x. Negative 1 times a negative 3 is a positive 3. Parentheses, subtract. Negative minus positive cancels out to add to be 0. Negative 3 minus 3 gives me a negative 8. So this gives me x minus 1 plus negative 8 over x minus 3. So this would be my r of x, just a different format of what I've had before. So this first part, the x minus 1, is going to be y equals x minus 1 is going to be the slant asymptote. Now we're going to graph it as y equals mx plus b, right? So it's going to be y equals 1 over 1x minus 1. So the rise over run is going to be 1 over 1. The b is a negative 1. So now we're going to find the numerator and the denominator, and we're going to decide what we do with that. So we're going to factor. So I get x and x, 5 and 1. The 4 is negative, so the larger number's got to be negative, so it's going to be negative 5 and a positive 1. Negative 5 plus 1 gives me negative 4, and my x minus 3 stays on the bottom. So our x-intercepts. So this is the part where we talked about before, same kind of thing. So we're going to find our x-intercepts. Now, what did we say to find x-intercepts? We set the numerator equal to 0. Because we want y to be 0. So that's going to give me x minus 5 equals 0 and x plus 1 equals 0. So x equals 5 and x equals negative 1. So this gives me 5, 0, negative 1, 0 are my x-intercepts. My y-intercepts are setting x equal to 0. So if I set all the x's equal to 0, 0, 0, 0, then this is going to give me negative 5 over negative 3. So my y-intercepts, x equal to 0 is going to give me y equals 5 over 3. My vertical asymptotes, is going to be setting the denominator cannot be 0, so x cannot be 3. Now, what about horizontal asymptotes? Well, if we go back to our formula, this is the degree m is greater than n. So that's the one where if n is greater than n, then we do not have a horizontal. So n is greater than m, no horizontal asymptote. But what do we have? We have a slant asymptote instead. So now we're going to graph. So our first thing, our slant asymptote, we're going to go down to 1. And then up there, up 1 and over 1. So up 1 and over 1. So we're going to dot in that slant asymptote. And then we also have no horizontal asymptote, but we have a vertical asymptote at x equals 3. So we have a vertical asymptote at x equals 3. So we can see that the asymptotes have crossed each other. So we're going to have this little pie-shaped piece. Okay, we also know we have a y-intercept of 1 2/3. So it's going to be approximately here. And we have x-intercepts at 5, 1, 2, 3, 4, 5, and negative 1. So we're going to go ahead and try a few test points. So my test points are going to be negative 2, which brings me out here, and positive 2, which brings me right in here, and a positive 4. Now to save time, I'm going to go ahead and tell us, so this is negative 1 2/5, this is 9, and this is negative 5. So just get these by plugging it into the original equation. So negative 2, negative 1 2/3, or 2/5. Bring me down here approximately, 2, 9. So 2, 9 is going to be up here. And 4, -5. So we can kind of draw in, let's go ahead and extend this a little bit further. So it's going to be kind of coming like this and then curving. So this side's going to come like this. And then this side's going to come like this. So it's coming on both sides approaching the asymptotes. So we've got slant, we've got holes, we've got asymptotes, we've got intercepts. So thank you very much.